Today we will test the PCB in 13 different ways to determine whether it is working properly or is faulty. The customer has complained that this Gree unit is showing AU5 error. Whenever AU5 error appears, it usually means there is an AC current detection circuit malfunction. The customer has sent us these two PCBs, one from the outdoor unit and one from the indoor unit. Now to test them, I've directly connected power to the board. As you can see, I've plugged this wire directly into the socket, and I've also connected a reactor to it. Now we'll flip the PCB and proceed with the testing. Now the first test we will do is check the AC voltage using a multimeter. So we'll set the multimeter to AC voltage mode, and now I'm going to turn on the main power supply. I've turned it on, and as soon as I powered it up, these 4 LEDs turned on, and they're running continuously. Now here's something important. When the outdoor unit is not connected to the indoor unit, there won't be any communication between them. Keep this in mind. In such a case, DC voltage will not be generated, and I'll show you later how to check that. But before that, notice the system has already started showing a fault, but we won't focus on that for now. We're just doing the testing. Our first point will be checking the AC voltage, because the problem here is U5, which indicates an issue with the AC current detection circuit. That's why we'll first check if the AC voltage is properly reaching the board or not. As you can see here, neutral is written at 1 point, so we'll check that point. The second point is marked L for line. We'll place the probes here and observe the reading. You can see that it is showing 240 VAC, which means our main power supply is properly reaching this point. The next test we'll perform is this. As you can see, there is a fuse connected along the line. So now we'll do the second test. We'll keep the negative probe on the neutral point and check the voltage at the fuse to see if the reading is correct. You can see that 242 VAC is reaching here, which means the fuse is also working properly. So, that completes our second test. Now the third test we need to perform is checking the DC voltage, and we'll do that on this bridge rectifier. This bridge rectifier is used for the SMPS, and it converts AC voltage into DC voltage, which supplies low voltage to the PCB. So let's check it now. We'll switch the multimeter to DC voltage mode, place the probes, and you can see here that it's showing 330 volts. The expected range here is between 310 to 350 DC volts. If the voltage falls within this range, it's considered excellent, and there's no issue. Now that we've completed that test, let's move on to the fourth test, which we'll perform on this capacitor. This capacitor is used to generate around 56 volts for serial communication. If it's generating voltages like 52 volts, 54 volts, or 56 volts, then it means it's working perfectly fine. So let's check if it's generating DC voltage. As you can see, it's currently generating 59.2 DC volts, which is acceptable. Once communication starts, the voltage might drop a little, but it usually stays between 56 and 60 volts while operating. So that completes our fourth test. Now let's do the fifth test. I'll show you the capacitor number related to serial communication, so we'll turn the PCB upright to locate it. Here it is, C24. You need to check the 56V serial communication voltage on this capacitor. Next, we'll check the voltages on capacitors C40, C82, and then C225. We'll check what voltage is present on each of these. Let's start with C40. We should be getting plus 12 volts here. When I place the probes, we can see plus 12.58 volts, and it's completely stable, which means this is acceptable and there's no problem here. The next test is for capacitor C82, which I've already shown you earlier. Let's check it now. We should be getting 5 volts here. As you can see, it's showing 5.04 stable volts with no fluctuation, which means the 5 volt supply is stable here. After that, we'll test capacitor C225, which I also showed earlier. We should be getting 3.3 volts, but it's showing 3.285 volts, which is acceptable because there's no fluctuation, and a small difference like this doesn't make much of a difference. All the voltage tests we've done so far are very important, but the one I'm about to show you now is even more critical. If you don't check this properly, you won't fully understand it. And if you miss this step, there's a high chance you'll make a mistake somewhere in the repair process. So please watch this test very carefully. This test is for the serial communication circuit. In this area, certain voltages related to serial communication are generated. Since the indoor unit is not connected right now, and we're checking the circuit voltages directly, let me show you what voltages you should expect here. I'll power the PCB on again because I had turned it off earlier. When you're checking this, don't hesitate to turn the PCB on and off. That's actually better, as it helps you safely observe the voltages and also prevents your hand from accidentally causing a short circuit. Here you can see a resistor labeled R73, and similarly, there's another resistor labeled R75. You need to check both cross sections, meaning both sides, of these resistors. Here's how to do it. We'll take a ground reference from this capacitor, C23. Place the ground probe there, and then check one side of our 73. You'll notice some fluctuation here. Now check the other side of our 73. Here, the voltage is fluctuating between 0 and 1, then back to 0. This is exactly how it should behave. It should fluctuate between 0 and 3.3 volts. If it stays within that range, it means it's working correctly. Now let's check the second resistor, our 75. As you can see, it first went to 0, then 2, then 1. This kind of fluctuation means it's also working fine. Now when we check the other side of our 75, the voltage is stable and looking good. So everything is working properly here. Now we'll perform the next two tests. One will be on U12 and the other on U15. These tests can be done from this side or by flipping the PCB. Both of these are optocouplers used in the serial communication circuit. But here, we specifically want to check whether voltage is being generated at these points or not. So I've flipped the PCB to check more easily. This is U12, and on the other side is U15. For U12, we'll place the probes on pin 1 and pin 2, and as you can see, the voltage is fluctuating between 0 and 1. This fluctuation should ideally be between 0 and 3.3 volts. If the value lies within this range, it means this part is working fine and there's no issue. Now, in the same way, we'll check U15. You need to check pins 3 and 4 of this IC. So, we'll test here as well. I'm turning off the PCB for now because the fluctuation has stopped. And that's because when there's no serial communication between the indoor and outdoor units, this signal won't fluctuate. But once communication begins, the fluctuation will start again. Right now, I'm testing without the indoor unit connected, so this kind of situation is expected. Now I've turned the power back on, and on U15, we are getting 1 volt stable. And that's fine, because at this point, there's no communication happening between the units, so 1 volt is considered normal. Once we connect the indoor unit, we can check this voltage again. But for now, with no connection, getting 1 volt is expected and completely fine. So far, we've performed 11 tests. Now we'll move on to the 12th and 13th tests. But these can only be done after we connect the indoor unit to the outdoor unit. Why is that? Because this PCB is designed in such a way that until communication between the indoor and outdoor units begins, it won't perform switching. There is a main relay on the PCB that handles the compressor's load. This relay is installed to ensure that the compressor starts softly, so the PCB doesn't get overloaded. Many of my viewers who work in this field probably already know that you can hear a tick sound. That sound comes from the switching relay. This switching relay helps soften the system's operation and make it easier to start. Another purpose of the relay is to give control to the microcontroller. So in case of any fault or emergency, the microcontroller can shut the relay off and disconnect the system to prevent any damage. Now I've properly connected the indoor and outdoor units, and we're going to power it on. As soon as I give it electricity, you'll hear the switching sound. I'll show you that too. Now, as soon as I powered on the unit, the lights turned on and the fan motor started running. But the switching sound has not occurred yet. So let's check the voltage in the meantime. This test isn't part of the main 13 tests. I'm doing it temporarily just to see whether switching is happening or not. We'll check the voltage at this capacitor, and it's showing only 58 volts. I've also confirmed that communication is active. Now, switching has occurred, though it took a bit of time before it finally switched. Now I'll show you the next test, and after that, we'll move towards diagnosing the fault. The next test is to check the voltages on the IPM. We'll check how much voltage is present between the positive and negative terminals. We'll use the multimeter in DC voltage mode. This is the positive terminal, and this side is negative. Here, we're getting 335 volts DC, which means the voltage on the IPM is correct. The next test can be done either on this diode 10 or directly on the IPM points. Let's check it first. We are getting 15.80 volts DC here, which is perfectly fine. There's no issue at this point either. Now, the rest of the test points are additional. We've already completed all 13 main tests. This part is extra. Be sure to check the 15 volts on the diode, and then test the IPM to ensure voltage is present at all relevant points. So we've already measured 337 volts, and now we'll check the U, V, and W pins inside. We are getting 15 volts there as well. Checking the next point, also 15 volts. And the next pin has the 15 volts again. This confirms that the IPM circuit appears to be working properly. I'm not seeing any fault in it. However, the compressor is not yet connected, and the green and orange lights are blinking. Let's see what kind of fault this is. It might be due to the missing compressor. Now we'll turn off the power. Now I've connected the compressor and also attached the analyzer. I'm going to power it on again. As you can see, I've powered it up, and it has turned on successfully. The display is working, and it's currently running at 16 degrees Celsius. We'll wait for a little while. The indoor fan motor has also started. However, the outdoor unit is taking a bit longer to start switching. We'll keep note of that. It's possible that the system is designed this way, to switch after a short delay. And now, as you heard, it has performed the switching and started the compressor. It has given the startup signal properly, and the compressor is now running. All the IGBTs are working fine, though initially the middle IGBT wasn't turning on properly. But no, look, it's on now. The issue was with the indicator lights. Now everything is working properly. The compressor speed is also stable, and the system is functioning without any issues. Now I'll turn it off, and we'll move on to checking the fault. Before I explain further, we'll first remove this heat sink. I'll show you what the actual fault is. Now let me tell you, when you encounter a situation where the unit is working completely fine, like I showed you, both the indoor and outdoor units are functioning properly, yet the customer is reporting a U5 error, then tracking down this kind of fault becomes quite difficult. Even now, I haven't personally seen the fault appear during testing. These kinds of faults are tricky to find, but I've worked extensively on this off camera. After a lot of effort, I finally found the actual issue, and I believe that this specific component is the cause of the U5 error. The person who sent me this circuit for repair also works in this field and had already tried to fix it, but they weren't successful because the error kept reappearing. That's why they finally decided to send it to me for further diagnosis. Now look closely. Some work has already been done on this board. You can see the diode has already been reworked, and soldering is visible here. The IGBT has also been removed once and reinstalled, but since there's no fault in the IGBT itself, the actual fault lies elsewhere. Let me show you. The problem is here, in the components labeled D902 and R901. These two are extremely important. Their function is related to charging the IGBT. Specifically, when the gate of the IGBT is turned on, it is crucial to discharge the gate properly. If the gate does not discharge correctly, it causes problems. This part of the circuit also plays a role in charging the reactor, and the charge gets stored in a capacitor, which then powers the rest of the system. But if the IGBT's gate is not discharging properly, it causes fluctuations in the DC voltage. When DC voltage fluctuates, the system assumes the AC input is unstable, and as a result, it fails to generate proper DC voltage downstream. When I check this resistor, R901, in resistance mode, it should show around 10 ohms. But when I measure it, it's showing 0.776 mega ohms, which is way too high. Off camera, when I tested earlier, it was even higher, but now it's showing slightly less. Still, this clearly indicates a fault. Let's go ahead and remove it to confirm whether it actually measures 10 ohms or not. Now let's check the resistor outside the system. As you can see, it's showing 0.667 mega ohms, which means this resistor has gone faulty. This is the actual reason behind the problem. When the gate of the IGBT doesn't discharge properly, what happens is that the system runs fine for a short time. But as soon as the speed increases, and it will increase, since the frequency ranges from 20 kHz to 49 kHz, this faulty resistor will stop functioning effectively. When that happens, the U5 error is bound to occur. Now I'll replace this resistor with a new one in the system and show you how much of a difference it makes. Now let's recheck the newly installed resistor to confirm whether it's working properly inside the system or not. As soon as I place the probes, it's showing 10 ohms, which means it's absolutely fine now, and I'm confident there won't be any further issues. Let's also check the diode once. Even though I believe it's working fine, it's always better to double check. It's showing 0.011, which is how it should behave. When you take it out of the system and test it, it should show proper values, but once placed back in the system, it might read differently due to surrounding components. Right now, it looks fine and is working correctly in its place. As of now, everything is installed back in the system. All components are functioning properly, the compressor is running smoothly, and the U5 error is no longer appearing. Click on the left or right thumbnail to watch our next videos, and subscribe. Thank you.